Good evening. Welcome to today's lecture. So good to see so many of you. Okay, I know the reason. So the quiz will be at the end of today's lecture, not at the start, right? So to not put some time pressure on anything, I just will do my lecture without any breaks today, right? So this means I guess we will, the lecture will end before, let's say, 9 or something. Then there will be some break, and after the break, the quiz will start, something like that. Okay, and the setting, I try to mimic the setting from the last quiz, right? So same time constraints, same number of questions, these kind of things. Content, of course, is different, you know that, right? Okay, which just should not be a surprise to you. So we can start with today's lecture without losing any time. So last lecture was a bit different from what we will do today. So last lecture was about optimal stopping approaches. We've seen basically American puts, American calls. We've seen these different notations, different notions of problems, free boundary problems. I guess you've prepared for the quiz, so you know what it is, right? Where the boundary is not exactly determined, but part of the problem to find a solution that actually tells you when to stop. That's part of the PDE, and then there's also this linear complementarity formulation that also specifies the two situations, which are always present in stopping problems, which are either stop or continue. So that's the complementarity formulation. Okay, so we forget about this for a second and we'll turn to something else, which is last time was a quite interesting class of problems. We were facing American options. Today we also face option pricing for non-standard options, so not vanilla options, European options, call options, put options. You have seen that, you know how this works, right? So this is no more interesting for you, but now we turn to another interesting class of options, which are called barrier options. So these are exotic options as well. So we talk here about exotic options. Exotic because they are not vanilla in the sense that they are not necessarily call or put options. They are related to call and put options, but they are not like vanilla call or put options. So therefore we call them exotic options. They are interesting, right? Because they are we will see some motivations. They are typically cheaper than classical call and put options, but also have additional features, additional properties. So, but they come at the expense of being more difficult to price. So today's lecture will only be about barrier options. So it will be something like an extended exercise, more or less. So there won't be much new concepts or nothing like new change of numeraire, nothing like that. It's just like an extended exercise over 47 slides or something like that, right? I could ask this kind of question. Of course, it's a bit too much, right? But I mean, you have all the knowledge to price these options, but of course there are a couple of new ideas, new tricks, and these kind of things, but it's just an extended exercise, more or less, what we will do today. Okay, and the one thing that might be new to you might be the reflection principle. I don't know if you have seen that before, but it's just some tool from stochastic analysis that we more or less need to price these options. Good. So what are barrier options? So barrier options, I told you, they are not call options, they are not put options, but they are linked to some payoff that could be a call option or put option. So we have some payoff that might be, typically is European. So it could be something like the payoff of a, let's say, call option, right? So this is what you should have in mind, but it's not only a call option, it's not a vanilla option, it's an exotic option. And why is it exotic? Because we have this additional feature of some barrier, B. So the second property makes it exotic. And so the thing is that the payoff is only paid under the condition that something happens with the barrier. So this can be either we hit the barrier before the maturity or we don't hit the barrier. So there are different conditions that can be specified So the barrier is just a number, right? So just a fixed number, and now we look at the possibility of hitting this barrier before time t. That's the thing we want to look at. Okay, so we specify this in a second, what this means, what are the different constellations that can happen, but in the end, everything happens conditional on whether we hit the barrier or we don't hit the barrier. And this makes the option path dependent, because this can happen at any time before maturity. I mean, at any time, you think of American options. It's not that complicated, because we can simplify this formulation a bit, as you will see later. So the two types of barrier options are either knock-in barrier options or knock-out barrier options. So knock-in means that we start away from the barrier, and as soon as we hit the barrier, the payoff becomes activated. So the option somehow starts in a dead state and becomes alive when we hit the barrier. For the knockout, it's just the other way around. So we start alive and we die whenever we hit the barrier. So these are the two constellations. So if you, I mean, just to make this a bit graphic, so let's say we have here some barrier B. It's just a constant value. So there's no fluctuation nowhere. And then we have our asset value. So this would be the situation that the barrier is above the initial asset price, but it can also be below, right? It can be specified in any constellation. It's just an example. And for, let's say we have a knock-in case, and then we end up below. So this would be time t, here's time 0. So if we have, let's say, a knock-in option, in this situation, the payoff would be phi of st, right? Because here at this point, the option becomes activated, and then we get the payoff. Even though at the end we land below the threshold, below the barrier, this doesn't matter. It just matters that there's one point where we hit the barrier, right? And let's say there is another situation where we end up here. Here the payoff would be 0, right? Because we never hit the barrier. We end up above the blue line, but the payoff is smaller because we have never hit the barrier before maturity. And for the knock-off option, the situation is just reversed. Once we hit the barrier, the option dies. We don't get anything. Okay. So these are knock-in options, knock-out options. And yeah, I mean, everything is possible, right? The barrier can be above the initial value. The barrier can be below the initial value. We just have to verify the condition whether we hit the barrier before maturity. But both is possible. So we can have a lower barrier or an upper barrier. And combining this with, I mean, we have either a lower barrier, either upper barrier, either knock-in or knock-out. We get 4 different combinations. So we can have an up and out. This means we start below the barrier, and the option dies whenever we hit the barrier, right? Up and out. As soon as we hit the barrier, it dies. Down and out is also, so this means just that the barrier is below, and as soon as we hit the lower barrier, the option dies. And then there are the 2 in constellations. Up and in just means that the barrier is above the initial asset value, and as soon as the barrier is hit, the option becomes activated. The option starts to live. And for down and in, it's just like the barrier is below, and as soon as we hit the barrier, the option becomes activated. Okay, so these are the 4 constellations. So let's look at these figures. Again, just some examples to showcase the situation. So here we have an up and in option, right? So this is the up and in situation. And in the left situation, the barrier is not hit. And this means the, I mean, here I write not exercisable. This just means the payoff is 0. Payoff is 0, and the reason is that we don't hit the barrier before maturity. And here it's exercisable. Again, we don't, I mean, it doesn't matter that the terminal asset value is smaller than this one or whatever. So here we hit the barrier before maturity. That's the important thing. And the option becomes activated, and the payoff would be, I mean, just the payoff of a call option. So the strike price can be above the barrier, below the barrier. All combinations are possible, right? So this means here you see we end up at some asset value that is above the strike. So the call option really has a positive payoff here. And here we end up also above the strike in the left situation, but the option is not being activated. Okay, so why? The question is, why do these kind of options make sense? Why could people be interested in that? So here the example is just, I mean, this was illustrated. I buy an at-the-money option. So at-the-money means just that the strike is the initial asset value, which is 100. Maturity would be 1 year, and knock-in barrier above, right? So this would be an up and in option, $120. And I mean, the left situation happens when we never hit the $100. The option becomes worthless. Otherwise, as soon as we hit the barrier, so this means from this situation on, so right of this point, it's just a regular call. So once the option has been activated, also the value should be the same as the one of a call, right? You cannot distinguish this anymore. Okay, and why do we want to trade in something like that? Because typically, I mean, they have to be cheaper than regular call options, than vanilla call options. On the other hand, of course, I mean, they are not, I mean, maybe there are some exceptions, but typically they are not traded on a stock exchange, right? They are much less frequently traded. They are less liquid than call options. But if they are traded, if you find an investment bank that sells you a barrier option, they are typically much cheaper than vanilla options, simply because we are not sure about the payoff, right? So the payoff is smaller than the one of a call option because it is the payoff of a call option in the situation that the barrier option is activated. Otherwise, it's smaller. If the option does not become activated, the payoff is smaller because it's 0, and the payoff of call option can be positive. So therefore, these options have to be cheaper. An example would be that today's asset value would be 100, and I mean, I'm confident, I have a strong investment belief that, I mean, the asset price will grow a bit, will increase, but not by too much, not crazy, right? That's a typical situation. And then we consider to invest either in a call option or in a barrier call option. And the call option, let's say, has a strike $105. Maturity is just like some toy values, 3 months, let's say. And this call option, you apply the Black-Scholes formula for call options, something like that, and you get $3. Okay, and then on the other hand, there's a barrier option with a knockout barrier. Right? This means if the asset price increases too much, you won't get anything. But if this doesn't happen, it's just the same as the call option. And because of this feature that we have this death option in the option, or this death opportunity, it makes it cheaper, right? So typically, I mean, these are just sample numbers, but let's say the price would be $2. If we hit the barrier 110 before maturity, then of course, if you think it will be larger than 105 but smaller than 110, you should buy the barrier option because it's cheaper and it's exactly fitting to your situation. This means typically you would do some scenario analysis and, compute probabilities for what you expect, and then accordingly buy the corresponding barrier call option. Okay, so you need to have a belief that it's unlikely that the asset price will exceed the 110, so that the asset price will be growing more than 10%, and then you save like 1/3 of your money. Okay, so that's the motivation, actually, why these options are traded in the market. First, you need to pin down what are your expectations, what you believe, and then you can invest in those kind of instruments. And the question is, of course, from the perspective of the sell side of the investment bank, what should you charge for these kind of options, right? So we want to, in the end, we are interested in the value of barrier option. Okay, before we delve too much into this, let's first try to understand the relation between down and out and down and in options and up and in and up and out. Okay, so we have a down and out call option, and we try to formalize the payoff of such an instrument. So we have a lower barrier. This just comes from the name down and out, right? So this means we start above the barrier, S0 is larger than B. And the payoff will be the payoff of a call option whenever ST is larger than B for all times. So ST being larger than B for all times just means the asset value never hits the barrier, right? We start above the barrier and the asset value stays above the lower barrier. I could also say this is the same as that even at the smallest value of all asset prices between time 0 and t is larger than b, right? Even the smallest value. So the minimum over all st is larger than b. That's exactly the same. Okay. If these two conditions, or if, there's another condition involved, right? So let's say this is just one condition. If this condition is fulfilled, then we get the payoff of a call option, which also can be 0, of course. And in the other case, if we hit the barrier, so this means otherwise means just that the minimum of all the asset prices is smaller than b. This means we have hit the barrier before maturity. Okay, so in the second situation, the option is worth less. Okay, and now, so I was rewriting the payoff in terms of its minimum, of the minimum of the asset prices. And so this means in total, I can just rewrite the payoff of the barrier option by multiplying it with some indicator function. So the indicator function is indicated on a set F. So the first condition, so this is the condition that the asset lands at some value that is larger than the strike. Only then I get a positive payoff. So that's the condition from the call option. And the second condition is that we never hit the barrier. The barrier is never hit. Right? So of course, only if both conditions are fulfilled, then my payoff is positive. If the first condition is not fulfilled, this just means that we end up below the strike, and then independent of whether we have hit the barrier or not, the call option wouldn't pay out anything, right? I mean, the call option only has a positive value if ST is larger than K. So this means the first condition just ensures that we end up in the money with the call option. And the second condition ensures that the barrier is never hit, that the option doesn't die before maturity. If those two conditions are fulfilled, then we get here 1, right? Otherwise 0. If we get 1 here, then the payoff is just ST minus K, which is positive. Otherwise 0. It's just the same formulation as the one we had here, but just written in a slightly more elegant way, because now it looks linear and it's just multiplied with an indicator function. Okay, that's very convenient as it turns out later, because I mean for option pricing, this is a formulation that we can work with. And option pricing means what we want to compute in the end is the price. And if I write price, I always mean the no arbitrage price, as usual in this lecture. In the Black-Scholes model, let's say, of a down and out call option. And this is denoted by DO. This is the index, and it depends on 4 inputs, which are the current asset price, the barrier, right, the strike, and the maturity. Okay, and this is specific to the down and out case. And now we can do the same consideration for down and in. So for down and in, we can also define some set f that we indicate on our indicator function that we multiply with the payoff. So that's the payoff of a call option multiplied with the indicator function f. And now same situation. So the first condition just ensures that we end up in the money with the call option. So say in the money condition for call option. Otherwise the payoff would be 0, right? And now down and in just means that we want to hit the barrier before maturity. This means there needs to be at least one asset value that is smaller or equal than b. This means the smallest value needs to be smaller or equal than b. If it is one asset value, then certainly the smallest, right? Okay, we just need to look at the smallest value. The smallest value needs to be smaller or equal than b. So the second condition just tells us that we have hit the barrier before maturity. Hit barrier before maturity. Okay, and the price of this option, I mean, it's the same kind of inputs. Difference is only in terms of notation would be down and in, DI instead of DO for down and out. Good. So not much has happened so far. I've just defined a couple of things. And now we want to look at how they relate to each other. So we have on the one hand down and in options, on the other hand we have down and out options. So we could think of just investing in both of them. We buy one down and in option, we buy one down and out option. Okay, so long one down and out and long one down and in. And then we just wait until maturity. And there are 2 situations that can happen. Either we hit the barrier before maturity or not. Right? It's binary. Either it happens or it doesn't happen. In the first case, that the barrier gets hit before maturity, the down and out option, I mean, dies before maturity because the barrier got hit, and we don't get any payoff. For the down and in, it's just the reverse situation. If the barrier gets hit, it becomes activated, and we get our payoff. So this would be just a payoff of a call option. For a down and out option, if the barrier never gets hit, we get the payoff of a call option. And on the other hand, this just means that the down and in option never gets activated. So there's a 0 payoff. Okay, so this is, what does this mean for our portfolio? If we hold the down and out and the down and in option, then in both situations we get the payoff of a call option, independent of what happens before maturity, whether we hit the barrier or not. In both situations we get the payoff of a call option. So this means the payoff of the portfolio is always that one of a call option. So this means if we hold both, we can mimic the payoff of a call option. So by no arbitrage, you can argue, okay, if that portfolio gives me the payoff of a call option, also the values have to sum up to the value of a call option. Otherwise, you could replicate and exploit arbitrage. And you can do this kind of argument I mean, not only for call options, of course, right? So, I mean, in this argument, I never used that actually I have here the payoff of a call option. I could just replace this by something else, some payoff of your choice. And so in general, we have here that the payoff of a down and out option plus down and in option, and option can be anything, they sum up to just the payoff of the option. So in total, we have that knockout option plus knock-in option just replicate a standard option, and also their prices sum up to the price of a standard option. I don't need a lot of mathematics here for these arguments. It's quite simple. Okay, and this is called in-out parity. Right? Down and out, in, out, parity. So this corresponds somehow to the put-call parity, but actually it's much simpler, right? So you don't need to remember the formula at all. It's just all you need to remember is like the table I have shown you before, right? If you sum them up, you can always mimic the payoff of the corresponding option. Good. Yeah. So what we want to do is we want to find the price of a down and in option. And this is enough, right? Because now we know that down and in option price plus down and out option price give us the price of a standard call option. And the price of a standard call option can be computed by the Black-Scholes formula. This means in order to get the price of a down and out call option, I just need to know the price of a down and in and the price of a call option, and I can just use the in-out parity and get it. So I can focus on one of those. I just decide on the down and in. I could also do the down and out. Doesn't matter. Good. So this is the formulation we have seen. Again, this should be some option that becomes activated as soon as we hit the lower barrier B. That's a down and in option. So the lower barrier B means that B is smaller than the initial asset price S, which is the first input to the option. On top of that, we have a strike price K, on which we don't assume anything. It can be above B, it can be below B. So all is possible. And T is the time to maturity. Good. I mean, straightforward approach to the price of anything, I mean, any type of option is always to look into, I mean, this would always be, if I would have no idea and would not think too much about it, just apply risk-neutral valuation. It always leads to something, right? Maybe not always the most elegant way, but I mean, typically it leads to something. So we also want to start with that one. This means risk-neutral valuation just means I need to discount the payoff and compute the expected value with respect to the payoff of the option. And this is the payoff of the down and in option. So this is payoff of down and in. And here 1F should indicate the same two conditions that we have seen earlier. So first, that the call option pays out something. This means that we end up in the money. So this is the in the money condition, as before. And down and in means we need to hit the barrier before maturity. This means the smallest asset value should be smaller or equal than B. For down and out, it would be larger than B. For down and in, it needs to be smaller or equal than B. So the second condition means hit barrier before maturity, before time t. Okay, and now you see why this formulation using this indicator function is something very elegant, very convenient. Because if I want to compute this expected value, this is what I want to do. Then I can just, I mean, now I have a linear object, right? There's no plus sign anymore. I don't need the plus sign anymore because the plus is now contained in the first condition. Otherwise, I don't get anything, right? So that's just saying I can multiply with the indicator function. It's similar to when you were computing the price of a call option in the Black-Scholes model for a Black-Scholes formula. In order to compute this explicitly, what you did was to indicate on this condition as well, and only to integrate from k to infinity, right? It's the same thing, more or less. So that's what I'm doing here, and this allows me now to write this. I mean, this is the same as to say, st indicator function f minus k indicator function f. Okay, and this linearity of the indicator function. Just some multiplication. I can do that. I mean, if you don't believe me that, you can just verify what happens if the indicator function is 1, then we get st minus k. This is true for both the above line and the line below. And if it's 0, then also the below expression is 0. So it's really the same thing. Good. This means I can now apply the linearity of the expected value, and I get this right-hand side. And this is very convenient now, right? Because now you see all I need to do is just to compute 2 expected values. I mean, still, what makes it a bit troublesome is like the multiplication with the indicator function. But still, I mean, it simplifies a lot to do that. Okay, and I've started using risk-neutral valuation. This is something that works for the second expression, but not very well for the first expression, as you will see. So for the first expression, by the first term, I mean this one, right? So this is my term 1, this is my term 2, this is the first term, and this is the second term I'm talking about. So the first term, I can also write that as b0 times the expected value of st times indicator function divided by bt. I mean, b0 divided by bt is just e to the power minus rt. Right? It's the same thing. And now I can, of course, also do this for the second expression. But for the second expression, it actually doesn't simplify anything. But for the first expression, I mean, if I write it down in this way, it should ring a bell, hopefully. 2 weeks ago, or 3 weeks ago, we were discussing exactly expressions of this kind. Right? Change of numeraire should come to your mind, because now what you see is for any numeraire, if I apply change of numeraire, CON, this is the same as N0, whatever the numeraire N is. Then I get a new measure QN, ST divided by NT times the indicator function. And more or less we have seen already what would be the reasonable numeraire in this situation. I just choose numeraire N to be S, and then I get S0 times the expected value with respect to QS times the indicator function on F. And this is an easier expression, right? And for the second term, I mean, there's nothing to do. But it's not a problem because, I mean, K and BT are just deterministic values. So in the end, this is also just a computation of the expected value of an indicator function. So this is the same as e to the power minus RT times K times the expected value of the indicator function F. So in the end, what I need to do is just to compute the expected value of indicator functions under 2 different measures. Okay, so here I've written down, again, the change of numeraire formula, but I mean, more or less it's just what is standing here. I mean, the value process divided by numeraire is a martingale, and if I choose as a numeraire the asset price itself, I get that V0 just S0 times the expected value of ST divided by ST. Here the indicator function keeps standing. We still have to do something, right? I still have more than 20 slides, no worries. But yeah, it already simplifies a lot in the beginning. So in the first equality, here BT as a numeraire and here S as a numeraire. Okay. It's just a summary of the previous slides. So this is my expression, just to label it correctly. This is my first term, right? Yes. This is my first term, number 1, and this is my second term. So in the end, I told you expected values of the indicator function, but expected value of the indicator function is always like 1 times the probability of the set f being attained plus 0 times probability of the complement of f, so just the probability of f, right? This means the structure of both terms is more or less the same. In both situations, we need to compute just probabilities of some set f. That's all we need to do. Of course, QS and Q are not the same, but more or less it's the same problem, up to slight differences in the probability measure. Okay, so this means the price of the down and in option is just S0 times the probability under QS of f minus the discounted value of k times probability of f. Good. So that looks much better now, right? So this means what we need to determine really is the probability of the set f under these two probability measures. So we have seen it was lecture 8 in one of it was an exercise, I gave it the title of an exercise, that if you change to the numeraire s, then you can apply Gersonov and multiply the exponentials, and you get a nice formula for the change of numeraire, how the drift changes when you change the probability measure, when you change the Brownian motion accordingly, and you get a new drift of r plus sigma square. So this is true under the probability measure QS. So this is a Brownian motion under QS. Okay, and this is a Brownian motion under Q. This is a Brownian motion under Q. And this is just the standard evolution of the stock price under the risk neutral measure that you have learned about, I think, the first time in lecture 6. In lecture 7, you have seen, okay, why this is the case when you apply Gersonov, but by using no arbitrage arguments, you already have seen with the Feynman-Katch application in lecture 6 that the evolution of the stock price under the risk neutral measure Q needs to be of this shape. So we have these two geometric Brownian motions, and the only difference is the drift is slightly different. So we have here a different drift from here, and now we just give this some global variable, let's call it eta or something. And then we say, okay, more or less it's the same type of problem. The only thing we need to replace is later our variable eta. But we want to compute the probability of something, and in these two cases, it's almost the same thing. I just need to replace r with r plus sigma square if I want to switch from one to the other probability measure. Okay, and if I look at my actual problem that I have, the problem I have is to compute the probability of f. This is my set f. Okay, f is just consisting of two inequalities. The inequalities involve ST, the asset price. ST, I know a lot about ST, but still it's not super convenient. I mean, if I have an inequality, in particular the second one looks a bit nasty, right? I have the minimum of ST smaller than B. I can simplify the problem, and this is valid, by considering log prices. So if I don't destroy the inequalities when I switch to log of ST, right? And I get something like log of ST being greater or equal than logarithm of K, and for the minimum, the same. I don't destroy the inequalities. And the log prices of ST, I will show you this in a second, look much nicer than ST itself. It's just a scale Brownian motion, so to say. And this allows me to compute the actual probabilities. Okay, let's do this. So it's more convenient to consider log prices, and again, we don't destroy the inequalities by doing that. So we have two situations. We need to compute the probabilities under QS and under Q. Again, it's almost the same thing. So what I have is, in both cases, I have that ST, something like S0 times e to the power, and now I have eta minus 1/2 sigma square t plus sigma wt. And eta, I just don't want to write down the same equation 2 times. It just is r in the second case for q, or r plus sigma square. Let's use the same color, and it becomes clearer. Right? It's a placeholder for whatever you want to use. So we have this representation. Geometric Brownian motion in the end. Good. And now you see what happens if I apply the logarithm to both left-hand side and right-hand side. So I get the logarithm of ST is the same as, on the right-hand side, I have the logarithm of a product. This is just the sum of the two components. So I have logarithm of S0 plus logarithm of the exponential. So this just becomes eta minus 1/2 sigma square t plus sigma wt. Okay, and this is much nicer, right? I get rid of this exponential term by applying the logarithm, and this just means that the dynamics of the log prices are just given by, again, I need to use this eta, minus 1/2 sigma square dt plus sigma dwt. Okay. So I don't have, on the right-hand side, any ST anymore. So it's not a geometric Brownian motion, but just something like a generalized Brownian motion. I just have an additional drift term and some scaling of the Brownian motion in the end. It's much simpler. I mean, you could also apply Ito's lemma to the logarithm. It leads to the same thing. I mean, I just get the derivative of ST, which would be 1 over ST, dST minus 1/2, 1 over ST square, and here the quadratic variation, so this would be an application of Ito. And then you just input the dynamics of ST, so 1 over ST times ST. Now again we have the eta dt plus 1 over ST sigma dwt minus 1/2 1 over ST square times ST square sigma square dt. Now all the ST's cancel out. And we end up with the same expression as before, which is just eta minus 1/2 sigma square dt plus sigma dwt. Okay, so it's the same thing as here. And I mean, you just need to input eta. Then in the case of Q, you need to just write it down. In this case, eta is just r. In the second case, eta is r plus sigma square. And then you get correspondingly different coefficients for the drift. Okay, so that's a bit more convenient than to study the acid prices itself, because we don't have like this nasty ST in front of the Brownian motion. In the end, it's just something like a Brownian motion. And the Brownian motion is a much easier object than the geometric Brownian motion. Okay, and now we can transform these inequalities by applying the logarithm to everything, actually, to make it inequalities that depend on the log prices. Okay, so our f, as before, and this is the starting point, the in the money condition and the hitting the barrier condition. Good. Then we apply the log price to, just to the left inequality and also to the right inequality. I mean, the minimum of ST being smaller or equal than the barrier just means we hit the barrier once, so this means there exists some ST such that ST is smaller or equal than B. Or there exists some time t, right? There exists some time t between 0 and capital T such that ST is smaller or equal than B. Okay, and this means, it just means I need to look at this inequality. There exists some time between 0 and capital T such that, and the logarithm is increasing in monotone, so log of ST is smaller or equal than logarithm of B, and this means I can also write this in the same way when switching to the minimum of the log prices. Okay. So if I give this the name star, this just explains this equality. Okay, and so can switch here to the to log inequalities. And now what happens if I switch to log prices? I mean, if we look at this equality, I still have the initial value, right? I don't start with 0, but I start with the logarithm of S0. So I just, in order to start from the value 0, I just subtract the initial value on both left-hand side and right-hand side, here and here. That's all I'm doing from the second to the third line. Okay, in this sense, it looks more complicated, but in the end I have simplified the equations. The expressions I get are much easier. The notation looks more complicated, but what is behind is much easier now. Okay, I just switched the notation to really show you, so that you start believing me what I tell you, that everything now is easier, actually. Okay, so xt is my new object on the left-hand side. So this is my xt here. And xt should be greater or equal than my x. And this object is something I want to call mt, and this here is m. Okay, this is the notation I'm using. So xt is the log price minus its initial value. mt is the minimum of the log prices until time capital T. X is the right-hand side of the first inequality, inequality, and m is the right-hand side of the second inequality. This means f in the end can be written as xt being greater or equal than x, mt being smaller or equal than m. So still the meanings are the same, right? So this is still call in the money, and this is still barrier is hit before maturity, before time t. So the meanings didn't change. I just transformed the inequalities. Good. And we have seen that xt are almost the log prices. So just what I've written down here is not exactly xt, right? On the left-hand side, we have the logarithm of st. But now to come to xt, I need to subtract the initial price. So this means xt is just what is standing here. So this part is xt. Okay, it's a very, very simplified expression, much easier than a geometric Brownian motion. So xt is now independence of which measure we consider. Just something like, we need to change the eta accordingly. We have seen that. Change the Brownian motion and change the drift. And here we have just some constant times t plus sigma times the Brownian motion. Here the same. Drift times t plus sigma times the Brownian motion. Just a Brownian motion times some t. That's actually a very easy expression. More or less, we study now just Brownian motion. Okay, that's why we did that. Good, and we have the case of a down and in option. So we are in the situation of a lower barrier. So this is a down and in option. So this means a lower barrier. This means b is smaller than S0. This means in particular that logarithm of b is smaller than logarithm of S0. This means in particular that m is smaller than 0. Yeah. So this means what we are now considering is something like this. So we have some process xt that is starting at the value 0. That's our, so here we have time, first of all. Then here is 0 on the vertical axis. And here we have some m that is smaller than 0. And our process x is just Brownian motion with some drift and another volatility. So it's really just some kind of Brownian motion, and we are checking whether we hit the lower barrier m. This is what we do. This is the situation we have now. This is our process xt. And mathematically, it's the same as considering the geometric Brownian motion. That's what we have seen. Good. So what we didn't compute anything so far. We just transformed the problem into an easier problem, and now the next goal would be to really solve this problem, to be able to compute something. So in the end, what we want to do is we want to compute this probability. So Q star is a placeholder for either QS or Q. But for both cases, we want to compute the probability of F, and this is the same as computing the probability of xt being greater or equal than x, and mt being smaller than or equal than m. Xt, we have seen, okay, this is the log price minus its initial value, is of the form eta t plus sigma times some Brownian motion. And again, I'm using the star notation, star being a placeholder for either the Brownian motion under Qs or under Q. So just some Brownian motion, depending which one I'm using, depends on the measure. Okay, we have seen the different etas, the different drifts for the different situations. So in the first situation, we have eta being r plus sigma square 1/2. So now, sorry, it's not very consistent with what I was using earlier, because earlier I was using eta to be r or r plus sigma square. So now I'm just relabeling this. So sorry, just to make this clear, maybe I write here, later this will be eta. Okay? Later this will be eta. So it's not exactly the same thing I was using here. Maybe I'm just using here in all places I've used this eta tilde. I mean, it's the same kind of consideration, just using some placeholder. This is my eta tilde, eta tilde. Okay. So later this will be eta, and eta tilde is just subtracting or adding sigma square half from that. Okay. But anyways, what we have is something times t, and the something depends on being under Q or under QS, plus sigma times Brownian motion. And now we have two situations. So the first one is this one under QS, and the second one is under QF. But we need to compute this in order to get the price of the down and in call by composing all the things together. Okay, it's just a recap that you, just sometimes step back a bit to know where in the proof actually you are. Again, it's just an extended exercise, and all we did so far was to realize that we need to compute this. We applied risk-neutral evaluation. We did some change of numeraire to the QS measure, and then we simplified the set F. That's all we have done so far. Good. And the expression we have now depends on xt. So mt depends also on xt. And xt is this thing that is actually not much more than a Brownian motion, plus some drift, plus some scaled volatility. And in order to understand the problem, what we first do is we assume we have a Brownian motion, so xt being a Brownian motion. This corresponds to the case that eta is 0 and sigma is 1. And then we solve the problem, we try to solve the problem, and then from having solved the problem in this case, we try to infer the solution for the second case. The second case is, of course, the case we are interested in, that, sigma is not 1, and eta is not 0, but we can get a solution for the second case from the solution for the first case. So we first want to study the case when xt is nothing else but a Brownian motion. Then later we just need to scale it and add some drift, and we get a solution also for the second case. Okay. This means what we now have is we face a Brownian motion or Wiener process, and what we want to do is we want to compute something like the supremum or the minimum of the process, the probability for the minimum of the process being smaller or equal than some value. Okay, this is something we need to compute. And this is something that is well studied for Brownian motion. So, and the trick is a very elegant, very nice trick that we are using that's called reflection principle. Okay. So we have a Brownian motion Wt, and Mt being the minimum of the Brownian motion. So more or less the same situation that we were facing before. And we have M being some value smaller or equal than some other value x. And now we are looking at the stopping time. Now you understand what this tau means after the last lecture. So it's the first time that the Brownian motion becomes smaller or equal than m. So the Brownian motion starts at a larger value than m, and we are looking at the first time we hit m. Okay, and so the situation is the following. So we are considering some small lower bound m, right? And some Brownian motion. And here is the first time where we hit where we hit n, let's say. And then let's say the Brownian motion becomes larger after that. And now the idea of what I will talk about in the next couple of minutes is that at this point here, what we actually can do is like we consider some reflected Brownian motion. So this means what I'm doing here is to reflect, to mirror the black path of the red one. So I have the original Brownian motion, which is my Wt. And I have the reflected Brownian motion, the red curve, that is being defined as, typically I use the notation tilde, which is the Brownian motion, the original Brownian motion, before time t, so 4 times t smaller than tau. So it's the same thing before time tau. But after I hit the barrier, I want to reflect it. So this means at hitting the barrier, it's the same thing. After that, the dynamics is just the opposite. I can achieve that by saying this is 2 times the value of the Brownian motion at the stopping time minus Wt for values larger than tau. Okay, so you see the value at, so W tau, this is just in this situation of the stopping time, this is m. So 2 times m minus Wt. At the case that Wt is also m, this is just m, 2 times m minus m. So this means we really start at the value m, and I mean 2 times m is just fixed, and after that it just evolves according to minus the Brownian motion, just with the shift of 2 times m. So it's really the reflected path of the Brownian motion. And now there are some results. You can show that this thing, Wt tilde, is also a Brownian motion. Okay. So, I mean, it's quite clear that, I mean, what happens for a reflected Brownian motion still has independent increments and all the properties of a Brownian motion. So this construction is really something reasonable that fulfills all these properties. If you want to prove that, you just need to look carefully at what happens exactly at the stopping time, right? That everything before that and after that is still independent and so on. But if you put this together, this is exactly the thing you obtain. We will not prove this here. This is just some result from probability theory. So if you want to look this up in one of the references, for example, there's this book by Protter. There you can find this result if you're interested in these kind of probabilistic results. It's quite interesting and so on, but we just use this result as some tool for what we have in mind. And you can more or less apply this to not only to this stopping time, but for more or less any stopping time. Okay, this is called the reflection principle. So the path after the time tau has the same distribution as the reflection of the path about the value n. So the red thing is the same. It's not the same, of course, but in terms of distribution, both are Brownian motions, and therefore have the same distribution. Right? Yeah. So this is just another illustration of the same thing. And now what we are looking into is how likely it is to achieve certain values. So here 2m minus w and here w. I will explain this on the next slide. And the assertion is that every path of the Wiener process of the Brownian motion, starting at time tau that ends at time t above x, has a reflected path that ends up at time t below 2m minus x. Okay, it's a bit complicated. I need to illustrate this. Okay, more or less similar picture as before. Okay, and here we have, tau is still the same tau as before. So tau would be the same, the first time such that the Brownian motion is smaller or equal than m. So we reflect our Brownian motion at m. Okay, and so at some point we are hitting m, and then there's some evolution. Let's say we start above at 0, and here we hit m for the first time. This means what we are doing here is a reflection of the whole thing. It looks somehow like this. So this is the reflected Brownian motion. So this is my W tilde, and this is my original Brownian motion. Good. Now what we want to check is that this blue path should end, let's say, maybe this too large. Let's maybe say here x. This path ends above x here, right? And now we are looking at the reflected path, and what we are doing is we are realizing, okay, this difference here is x minus m. And now I'm looking at the difference of x minus m, but starting at m instead of x. So this is just m minus x minus m. So this would be 2m minus x. M is negative. And then this path ends below this value, right? This is more or less the assertion, and if you want to formalize it, so we have the original Brownian motion, the probability of the original Brownian motion ending above the value x, given that, that tau happens before time t. This is the same probability than the reflected Brownian motion ending up above x, because both are Brownian motions, have the same distribution. And now I'm just using the definition of the reflected Brownian motion. So this is 2 times m minus the original Brownian motion ending up above x, tau being, this is a capital T here. Capital T. And now I just need to reformulate this inequality. So I'm putting Wt to the right-hand side. Maybe I should use capital T's here. Sorry, all of the T's are capital T's. Yeah. So it's capital T greater or equal than x, capital T, capital T. So I'm putting Wt to the right-hand side, and then I get Wt being smaller or equal than 2m minus x, tau being smaller or equal than t. So visually, you see, you can just consider 2 Brownian motions starting at this point, one being the Brownian motion, the other one minus the Brownian motion. I'm just starting at value m, and then, of course, it's the same probability that they end up above the same difference from 0 and below the same difference from 0. So more or less, this is just the assertion we have here. Okay, this is the reflection principle. That's very important, and this allows us to simplify things a bit. Before we do that in practice, let's do one exercise to get a bit more familiar with this principle and to understand why this actually can simplify expressions. So This is not exactly the expression we are considering later, because our expression is slightly more complicated. But what you see from what I have here in this exercise, in this assertion, is a simplification of an expression. So we want to compute the probability of the supremum of a Brownian motion being greater or equal than A. And I mean, if I ask you to do that, probably without the reflection principle, I mean, you don't know how to do that, right? But the expression on the right-hand side is something you can directly compute because it just involves the probability of a Brownian motion. You know the distribution of a Brownian motion is the normal distribution, so the right-hand side expression is much easier. And that's exactly the beauty of this reflection principle. It allows you to transform these complicated maximum, minimum expressions into easier expressions. Okay, then we just need to do the calculations for that. So I start with the left-hand side. So the probability of the supremum between 0 and t of the Brownian motion being greater or equal than A. And now what I'm doing is just to intersect with two possibilities. So either Wt is greater or equal than A or smaller than A. So this is the same as the probability that the supremum, so still the same thing as before. And now I'm intersecting with Wt being greater or equal than A. This is not correct yet. I also need to intersect with the complement. So it's the same as the supremum Wu greater or equal than A and Wt being smaller than A. Okay, so now I'm looking at the first expression. So the first expression is an intersection of two events. And the first one is that the largest value of the Brownian motion is greater or equal than A. And the second event is that the value at time t is greater or equal than A. But of course, if the value at time t is greater or equal than A, then always the largest value of the Brownian motion is also greater or equal than A. Because I know that the condition is already fulfilled at one specific time. This means the intersection of the two is just the probability of Wt greater or equal than A. So this is if Wt is greater or equal than A, then I know that the supremum of all the values is also greater or equal than A. So if I intersect the two events, I just obtain the first one that implies the second one. So the second, so in other words, the event Wt greater or equal than A is contained in the set that the supremum over Wa is greater or equal than A. And if I intersect the two, I just obtain the smaller of the events. Okay, so here, for the first expression, I got rid of the first condition. Okay, but the second one is a bit more difficult. Good, what is standing here is the supremum over all values of the Brownian motion is greater or equal than some value A. Okay, this means I can translate this into the situation we had before by defining some stopping time, tau, as being the first time, such that the Brownian motion is greater or equal than A. Okay, same situation as before. I'm just using the threshold A, and I'm considering the first case when I hit A. And then the supremum being greater or equal than A just means that tau happens before time t. So maybe I should use a consistent notation. So here I'm using, just to not confuse you, I mean it's technically correct, but it might be better to use u as an index. So the first time u, where wu is greater or equal than a. So this means if this happens before time t, then the supremum, I mean, one of the values was larger than a, and it's the same thing. So just to make this a bit more clear here, so all I'm saying is that if I hit the barrier before time t, then the stopping time is smaller than t, right? That's all I'm saying. So in this case, if this event here happens before time t, then the stopping time, which is here, so I'm translating the vertical axis to the horizontal axis by saying if I hit m before maturity, then tau, which indicates the first time when this happens, is smaller than t. That's all I'm saying. So this is the same thing as to say tau is smaller or equal than t. This happens really before time t. Good. And now what I'm doing is I have this intersection of two events. And now I'm just writing this as a conditional expectation, conditioning on the property that the stopping time happens before time t. To make this correct, I need to multiply with this event as well. And now I'm in the situation that I was already facing earlier, that in this situation I can switch to the reflected Brownian motion. The reflected Brownian motion, I mean, I can denote this by Wt, tilde, has the same distribution under this condition. We have seen that if this happens before time t. So this here is the reflected Brownian motion. Good. We have also seen how the reflected Brownian motion is defined. Here I'm reflecting at the value a, right? The first time I'm hitting the barrier a, so I just need to replace m by a, but it's the same. I mean, a is now an upper value, but it's the same construction. So the first time I'm hitting something, so I get 2 times a minus Wt being smaller or equal than a. Conditioning still on the same event, multiplying still with the same event. Now I'm transforming this into a probability independence of a. And you see what I get here is just the probability of Wt being greater or equal than a. Conditioning on tau before time t, probability of tau before time t. Okay, and this is the intersection of the two things. And then I'm just in the same situation as before. So this is the same as the probability of Wt greater or equal than a, and tau being smaller or equal than t. And this is exactly the same event I was considering here. So this is just probability of Wt greater or equal than a plus the probability of Wt greater or equal than a, and it's just 2 times the probability of Wt greater or equal than a. Okay, and I mean, of course, I need to argue, so just to make maybe the last step a bit clearer, so what I was using here in this step is also what I'm using in this step. Okay? So that this event is contained in the second one. That's also what I'm using here to come from this line to the last line. So overall, what I did was just using this property, the green star property, right? That if I'm at terminal time larger than the corresponding value, that this just means that I have already hit the barrier before that. And the second one was to switch to the reflected Brownian motion. That just allows me to switch to the same side of the barrier and to apply the same property again by using the reflected Brownian motion. Okay, this is very nice, right? Because this allows us to get rid of the supremum and turns out to be extremely useful. Okay, and now we want to apply this to our problem. So our problem is very similar, but not exactly the same. So we need to do one step more, let's say. Okay, so we have set A. This corresponds to, I mean, our situation is slightly simplified, but this corresponds to the F we have seen earlier. So the first condition, WT being greater or equal than X, is the in-the-money condition. The MT being smaller or equal than M is the condition on hitting the barrier before maturity. Good. So we have M being smaller or equal than X, and we are considering the first time where the Brownian motion is smaller or equal than M. So the Brownian motion starts at 0. We were assuming M is a smaller value than 0. So what we want to compute is the probability of A, which is the same as, I mean, just by definition, the probability of the Brownian motion being greater or equal than X, and the minimum of it being smaller or equal than M. Okay. Similar argument as before. So the minimum of all values, or of all values of the Brownian motion between 0 and t being smaller than m just means that tau has already happened before time t, right? This just means that, okay, I just explain it in words again. If the minimum of the Brownian motion is smaller or equal than m, this means the Brownian motion has hit the barrier m before time t. This means the time when this happens is exactly tau, happens before time t. Okay? It's just the same condition. So I really can replace mt being smaller or equal than m by tau being smaller or equal than t. Exactly the same condition. I'm not doing anything. And here what I'm doing is I'm just switching to the reflected Brownian motion again. So I'm just saying this is the same probability as the tilde Brownian motion being greater or equal than x whenever tau is smaller or equal than t. And I'm using the definition of the tilde Brownian motion, which would be 2m minus the Brownian motion being greater or equal than x and tau being smaller than t. Okay, and now I'm just solving for WT, and this is the same as WT being smaller or equal than 2m minus x, and I'm still intersecting with the event that tau happened before time t. Okay, and if now I need to look at these two events. So the first one is the Brownian motion ends up below 2m minus x. So 2m minus x, m is smaller or equal than x. This means 2m minus x in particular is smaller or equal than m. Right, minus x is smaller or equal than m, so I can just directly conclude that 2m minus x is smaller or equal than m. So this means that if Wt is smaller or equal than 2m minus x, then barrier has been hit before maturity. correct? This just means I'm ending up at some value below the barrier m. Okay, this means I actually don't need to consider the second event I'm intersecting with, because it doesn't impose an additional constraint, because it's already clear that if I'm ending up below some value, below the barrier, then tau automatically is always smaller or equal than t. Okay, I can omit the second condition. That's exactly the same kind of argument I was using here. So if Wt greater or equal than A, I was concluding the largest value. I'm now considering the same situation with the smallest value. If I'm ending up at some value smaller or equal than m, I know that I have hit the barrier before that. So I can omit the second event I'm intersecting with. And this means I'm just having a probability relating to the Brownian motion. Probability of the Brownian motion being smaller or equal than 2m minus x. The Brownian motion itself, is a very elegant, very beautiful object. I know the distribution. Wt is just a normal distribution with variance t. So this means this is the same as probability of, let's say, some x being smaller or equal than 2m minus x divided by square root of t, where x is standard normally distributed. We just need to scale to come to the standard normal distribution. And this object here then has a CDF, it's just the same as the CDF of standard normal distribution applied at the argument, 2m minus x divided by the square root of t. Okay, so this means in this situation, I have solved the problem. And the main argument here is really the reflection principle. Okay, and now the next step, more or less are just using these kind of arguments. But we need to bit more general in that case. And for this, we need that this equality holds. Why is this equality true? So A and B are just the sets I have defined here above. I'm starting with the left-hand side, right? So if I'm having the expected value of indicator function A and G is just some function, doesn't matter, it doesn't have a specific shape. It's just some function G. I want to use later a specific function, but this is true for any function G. If I'm considering an expectation of this form, and A contains the event that tau happened before time t, right? This is the second line here. This means what I can do is I can switch. So first, maybe let me write it out. So this is the same as Wt being greater or equal than x, tau being smaller equal than t, g of the Brownian motion. And now what I can do here in this step is to switch to the reflected Brownian motion, right? Because I'm conditioning exactly on the situation that tau happens before time t. So what I can do here is to switch to the reflected Brownian motion. If I do this for the indicator function, we have computed this, right? Then this just leads to indicating on the event b. And for the second case, maybe let me write it out. Otherwise, it doesn't become clear. So this is the same as to switch here to the reflected Brownian motion. Tau happening before time t, and g being here the reflected Brownian motion. And if I compute this, the indicator function, that's exactly the calculation we did here. Leads to indicator on B, and G, I'm just using the definition of the reflected Brownian motion, becomes 2m minus Wt. Just the same arguments, and I get this more general form. So I can also multiply with some function G. That's all I'm saying, and I get this equality. I will use this later. So that's very important. Okay, so I mean, we have solved the problem, but we don't have solved the original problem. We have solved the problem in a very simplified setting where we have assumed that our drift is 0 and that sigma is 1. Okay, now we want to switch to the more general case that we are actually interested in. So the case when xt is actually something like, I mean, xt still stands for the log asset price. And we have seen that it has this form, just eta t plus sigma wt. I mean, actually some very useful form, because now we can use the results for the Brownian motion and scale the object we have worked with, which is the Brownian motion, a bit, add a drift, and then try to get something. That's the idea. Okay, so the general case just means we assume this form, xt and mt, now is not the minimum of a Brownian motion, but the minimum of xs. So there's a bit of an abuse of notation. I'm sorry for that. I'm just using the same n. Okay. Good. So let's look at x. X is eta t plus sigma wt. And I'm writing this slightly different. I'm just factorizing the sigma. Why am I doing this? Because if I do write everything in this way, you see I'm isolating the Brownian motion. So there's no coefficient anymore in front of the Brownian motion in the second factor. And this is a shape that should look familiar to you. I mean, you have prepared for today's lecture for the quiz, right? So you have seen these kind of results. So this was more or less the assertion of Girsonov, right? If you apply Girsonov, what you get is that the Brownian motion plus something is the Brownian motion under a new measure. So this means if we can apply Girsonov in a convenient way, we should get, that's the hope, as a result that this is again a Brownian motion. So the question is, under which measure is this a Brownian motion? Because if this is a Brownian motion, then we can apply, under the new measure, the results we have derived earlier. Because then we are in a situation from before where we have assumed everything is a Brownian motion, and then we can just apply the reflection principle in the same way, and so on, and simplify everything. So that's the hope. And I mean, the question is not very difficult to answer. More or less, you know already what to do, but I will do this on the next slide. We just have to, I mean, more or less define kt being this kind of drift here, right? Okay, so the hope is that this object will be a Brownian motion. I call this W tilde. Again, sorry for the abuse of notation. So the tilde here is a Brownian motion. It's not a reflected Brownian motion or something like that. I'm just using whatever is convenient for the corresponding slide. Okay, so we want to compute this probability, just stepping back a bit. And the idea is exactly what I have described. We want to find a probability measure by using Girsonov, such that this W tilde here becomes a Brownian motion under a new measure or Wiener process, and then apply the same idea as before in the previous slides, so the reflection principle to that. We've seen how it works, more or less. There's nothing to compute. And then we have computed everything under measure p tilde, but actually we want to compute everything under p. So the final step will be some change of measure back to p, and then compute everything. So these are the three steps we are performing now. Okay, so the first step is really to find some measure such that this object W tilde becomes a Brownian motion under the corresponding measure. The idea would be to, I don't need to tell you, you know this, right? I need to apply Girsonov for that. Change of measure always means Girsonov. We want to define some change of measure. Notation will be LT as usual, such that DLT is just my usual kt, lt, dwt, so this will be my kt, dwt. Because if I do that, then the change of measure will be of this form, and this just means that the corresponding dwt, how should I denote this? Yeah, tilde, dwt plus plus eta divided by sigma dt is a Brownian motion, and the important thing is under the new measure, under p tilde, right? That's the assertion. So here kt would be minus eta divided by sigma, and if I subtract kt dt, I get a Brownian motion under a new measure. Subtracting means adding eta divided by sigma. Good. So I obtain some measure. I know how to change the measure. I just need to apply Gersonov, that's all. And then I obtain, just to show you where in the proof we are, that this object here is a Brownian motion under the measure p tilde. So actually xt is almost a Brownian motion. I just need to multiply with sigma under the new measure. Okay, I still want to compute this probability. Xt is not a Brownian motion, but almost, right? Xt is sigma times w tilde. In the end, I know what to do if there, instead of xt, there would be some Brownian motion standing. But right now, we have sigma times the Brownian motion. So what I need to do in order to get rid of the sigma is to divide the inequalities, both left-hand side and right-hand side, by sigma. Then I have a Brownian motion on the left-hand side, and then exactly the situation that I had earlier applies. Okay, I have this very nice factorization. This means just I want to divide everything by sigma, actually, right? So this means my mt that is standing here, mt is also the minimum of, just to be clear, doesn't hurt to be as clear as possible, it would be the minimum of xt, right? This is mt. This is not a minimum of the Brownian motion. It's the minimum of xt, and this means this is the sigma times the minimum. So just sigma is just a constant factor. Sigma times the minimum of the tilde Brownian motion. So I can divide everything by sigma. This simplifies the inequalities. The corresponding quantities divided by sigma is what I denote by m tilde and x tilde. And then I get, this is the same as what is standing here on the right-hand side. Good. And this is exactly the same situation as earlier. Just let me check with which slide it is. So that's exactly what is standing on slide 32. Same situation as on slide 32. I can apply the reflection principle. I can simplify the expression. I get an expression that only depends on the Brownian motion, doesn't involve the minimum anymore. This is due to the beautiful reflection principle. And the only thing that I need to do in the final step, this is actually, here I need to be a bit careful, right, with the notation. It is the probability of the Brownian motion, tilde, smaller than, and if I switch back to the m notation without the tilde, I need to realize, okay, what is standing here on the right-hand side is just 2m minus x divided by sigma. Okay, that's all. So I get this additional sigma here in the denominator. Okay, but apart from that, it's pretty much the same. Just the factor sigma is different. And now I can also apply, or I want to apply the result that we have seen earlier. So I was explaining that we can also do the same kind of transformation that I did here when I include a function g in the expected value. So that's what we have seen earlier. What I have explained is just like the same, I mean, no new arguments. I'm just applying the reflection principle again to the function g. Okay, and we need this because what we now have computed is not what we want to actually compute, right? Because what we have computed is the probability of the set f, but under the wrong measure. We have computed everything under the measure p tilde. Okay, we can compute it under the measure p tilde, but actually we don't want to do that, right? We want to do this under the measure p. So this means the final step would be to switch back to the original measure. Okay, so we want to switch back to the measure p, and p can be q or qs, right? So whatever we want to have later. So p is just a placeholder here. Good, and we, I mean, switching probability measures means Girsanov means applying these rather Nicodim densities. You've seen that before. And if I consider density dp over dp tilde, it's just the reciprocal of dp tilde over dp. So this would be 1 over LT. Right? I've defined LT earlier. This is what I had here. If I divide by this, I just get rid of the minus signs. The minus signs transform magically into plus signs. It's very nice. So there's, I mean, it's just exponential functions are easy to deal with, right? So we just get, this is 1 over LT. So I know how to change from one direction, then the other direction is also there. It's just 1 over LT. 1 divided by the exponential is just the exponential to the minus. This is what I have. And the relation between WT and WT tilde, I need to be clear here. I've defined it this way. So this is my WT tilde. This means WT is WT tilde minus eta divided by sigma times t, right? Okay, so this means this object is the same as WT tilde minus eta divided by sigma times t. If I plug this in, I multiply eta divided by sigma times t with itself, and I get here the same factor standing with 1/2. So 1/2 times minus 1 times the same thing is minus 1/2 of the object. So this means switching from WT to WT tilde changes this factor just by changing from a plus to a minus sign. Okay, and this is a function I can define, if I want to, independence of my Brownian motion W tilde. So this is what I want to call G. And G is not random here. Here I'm not abusing notation. Here I'm using it on purpose because I want to remind you that here is also standing a G. Right, so this will be my choice of G for this equation. Good, and now I can plug everything together. Good. So what I want to compute is really this expression. So P can be, in the end, Q or QS, as a reminder. So P is just a placeholder for whatever measure I'm using, and eta then corresponds to the corresponding drift. I want to compute this expression, so this is my probability of F. This can be written as an expected value of the indicator function of the same set. This is my indicator function A tilde. Just gave this name earlier. And now I want to switch to P tilde. Why do I want to switch to P tilde? Because under P tilde, I have computed already things, right? And in order to switch to P tilde, what I need to do is to multiply with the corresponding Radon-Nicodim density. So I mean, we've seen that if so the expected value of the indicator function a tilde, this just means I'm integrating over a tilde with respect to p. If I want to switch to p tilde, what I need to do is just to look at the corresponding density and integrate with respect to p tilde, and then this becomes the same as indicator function a tilde times the density. And here I'm integrating with respect to p tilde. So that's what I'm doing here. It's exactly the same thing I was explaining when I was discussing Girsanov. That's how you change probability measures, by multiplying with the corresponding adjustment of the weights of the probability measures, the ratio of the weights. Okay, and now I need to recall what I have written down here. I defined simply the change of probability measure as my function g independence of the Brownian motion tilde. But that's just my g w tilde. Okay, I can write it in this form. And now, in the next step, I'm just using this equality, which is the reflection principle, actually. So this means here in this step, this is the actual step where I'm applying the reflection principle. So I'm switching Brownian motions, so to say. I'm switching from the set a tilde to b tilde. If I say I'm switching Brownian motions, I don't mean I'm not switching probability measures, but I'm switching from the original Brownian motion to the reflected Brownian motion. That's what I mean. That's what I'm doing in this step where I'm applying the reflection principle. And therefore, Wt becomes 2m minus Wt. We have seen that before. That's exactly this step. And now I'm just writing out things. So my definition of G is just the definition that I had here. I can just now plug in, instead of W tilde, 2m minus W tilde. So that's what I'm doing here. And the definition of B tilde is the one we had here. It's just the Brownian motion being smaller than 2m minus x. Okay, so I'm just almost there, right? Because these are all expressions that, that don't depend anymore on the minimum or nothing like that. It only depends on the Brownian motion now. And by the way, if you are confused about where we got rid of the minimum, that's exactly in this step, right? Here we were switching from an expression involving the minimum, which is the a tilde. This involves clearly the minimum here, but the right-hand side does not involve a minimum anymore. So you see here only Brownian motion and constant values. This is quite nice because through this application of the reflection principle and a couple of other things, right? Of course, we need to be careful with the probability measures and the log prices and so on. We are now in a situation where we actually can compute things, because integrals with respect to the Brownian motions are just integrals with respect to normal distributions. I mean, I don't know how much you like integrating with respect to normal distributions, but I mean, you can do it, right? And that's exactly what we want to do. So we know that the Brownian motion W tilde just has a normal distribution. Again, the mean is 0, and the variance would be t if we consider the Brownian motion at time t. This means the PDF, a density function, would just be 1 divided by 2 times pi t times e to the power. Maybe let's use the same integration variable that I'm using on the right-hand side. So I'm writing this as a function of w. e to the power minus w squared divided by 2 times t. Yeah? So this means, so this was the expression we had on the previous slide, what is standing in the first line. So I didn't do anything here. And by changing from the first to the second line, I'm just writing the expression as an integral. So first I'm transforming the indicator function into my integration boundaries, right? I'm integrating the w from minus infinity to the upper bound, which is 2m minus x. And I'm multiplying the expression simply with the PDF. The PDF is what I've written down here. It's just a PDF of a normal distribution, not a standard normal, but I need to account for the time component as well. So it's a normal distribution with a variance t. Okay, so that's the integral I need to solve. And that's not very exciting, but you can do it again. So I need to look at this expression I have. And I mean, almost every time you need to solve something like that, it's something like completing the square and applying binomial formula, right? And then in the end, you hope to transform it into an expression that is easier to solve, that is easier to compute. In the end, the best case would be you don't have to integrate anything because you get some expression that you are familiar with, something like an integral over a standard normal distribution, which you know is just like the CDF of a standard normal distribution. Then you can write it down in terms of a CDF of a standard normal distribution. More or less, that's what I'm trying to do. So I'm trying to convert this into a simpler expression. Okay, the first step, again, that's also like a tip for exercises and so on. If you ever need to compute this kind of integrals, and it can happen in the Black-Scholes model, that you need to compute option prices by solving integrals. I mean, very often it's just applying binomial formula, completing the square, and these kind of things. So here, and from this to this step, from the second to the third line, so first of all, if I'm just using that n tilde and x tilde are just the values divided by sigma, okay? And I'm just completing the square here by applying the binomial formula. So this is really an application of the binomial formula. You can just, so how you do this is just you look at the square values and then you more or less know what you expect to have when you apply the binomial formula, right? That's exactly what is standing there. If you write the binomial formula out, you see that's exactly the same as in the line above. Good, and I have this expression now. So I'm integrating with respect to w. And as I've told you earlier, so for these kind of exercises, it would be good to have something. I mean, you could try to integrate this directly. I don't know if it's possible, but here, something you can definitely integrate would be an integral over a standard normal distribution. I mean, you probably cannot integrate it, but you can write it down as in terms of a familiar expression, which is the CDF of a standard normal distribution. So therefore, the idea at this stage would be to apply some kind of substitution. So the substitution would be to replace this expression under the square, and we also include the t here. Because then what I get, you can already peek at the next line, right? Would be e to the power minus 1/2 c squared, which is just something like the CDF of a standard normal distribution, up to scaling factors. So this means the substitution would be z to be exactly what is standing here. So eta divided by sigma t plus w, and I want to include the t as well. So I divide by square root of t. Okay, this would be my substitution. Okay, I want to switch from w to z when I integrate. So my dw It's just the same as, I need to, the factor in front of w is just 1 divided by square root of t. So this is the same as, maybe let's do one intermediate step to make this clear. So I can write w as square root of t, I'm just multiplying, times z minus eta divided by sigma t, right? Okay, so this means my integration variable dw changes to square root t dc. Of course, I need to adjust the boundaries as well. So this means if I change from w to dc, I need to multiply first with square root of t. And second, I need to look at the upper bound here that changes. Because, w being smaller than 2m minus x divided by sigma. And now I'm using the definition of w, which I have written down here. Just means that square root t, z minus eta divided by sigma t, smaller or equal than what is standing here on the right-hand side. So I can also write this as z smaller or equal than eta divided by sigma t plus 2m minus x divided by sigma, and then I need to divide by square root of t. And this is the same what is standing here, right? So if I write this in a bit more concise way, I get 2m minus x plus eta t divided by sigma square root of t. So this is my new upper bound here. Good, so I'm switching to this integration variable, z, I'm integrating over z. I'm multiplying with square root of t when I switch from w to c, and this eliminates this factor in front, right? So I don't have it here anymore, and I just collect these constant values here in front of my integral. So maybe also to emphasize this, so these values here, they are now just standing in front of everything. And yeah, so I need to change the upper bound. I'm switching to z, and now I have an integral over the density of a standard normal distribution. And if I integrate over a standard normal distribution, this means I'm looking at a variable that has a standard normal distribution, which has a CDF, which I can denote by n. So I can just write everything as the CDF of a standard normal distribution and plug in the upper bound of the integral. So I didn't compute anything, but I have found a nicer form for it. So a standard form, right? And practical use would be, n is implemented everywhere. If you want to compute this value, you can just plug it in Python. There's a norm.cdf, and you can compute things, right? So that's a much more convenient form. It's an analytical solution for your problem. This means now we have computed almost everything. So we just need to translate this back to our original problem. Let's do this. So we have shown that this problem has this form. So this was exactly the result of the previous slide when we were evaluating this integral. Okay, and still the p is a placeholder, the eta is a placeholder, and so on. So we need to just bring it in the correct form. So how we started was this. So we wanted to compute the price of a down and in call option. We have seen this the same as what is standing here on the right-hand side. So we have QS and Q. F was defined in this way. So it was defined in dependence of the log prices. And I subtracted also the initial values of the log prices. Eta was defined either to be r plus sigma square half for QS or r minus sigma square half for QF. Two different definitions in dependence of which measure we are considering. And now we have this formula. So let's first look at what is standing here. So we have 2m minus x plus eta t. So if I'm translating this, so here I have 2m, m is defined in this way, x is defined in this way. If I'm computing 2m minus x, I have 2 times the logarithm of b minus 2 times the logarithm of s0 minus logarithm of k plus logarithm of s0. Okay, so what I obtain is 2 times the logarithm of b, and here minus 2 times the logarithm of s0 plus 1 times it, so this is just minus 1 times, so I have minus logarithm of s0 plus logarithm of k. Okay, 2 times logarithm of b is just logarithm of b squared minus the logarithm of, and now what I'm doing is just to use that the sum of 2 logarithms is the product of it, of the 2 arguments, so I have logarithm of s0 times k, and here I have the difference, so this becomes logarithm of b squared divided by s0 times k, right? So this is my, what is standing here, so this is my 2m minus x, which I had above. This is my eta here. I'm just plugging in eta for the first case, for the QS case. And then here, if I look at the exponent of the exponential function, I have 2 times eta times m divided by sigma squared. So this is my eta, this is my m. Right? M is the logarithm of b minus logarithm of s0. It's the logarithm of b over s0. Okay, and the last step would be to simplify the exponent a bit. I mean, everything is correct here. I mean, you could stop here, but you can write it in a slightly nicer way. Okay, let's just do this for the first case. So what I have here is e to the power 2 times r plus sigma squared divided by 2, logarithm of b divided by s0. I mean, what I can do is I have e to the power logarithm of b divided by s0, and here this expression, I mean, what I'm having here is just 2 divided by 2, so this is r plus sigma squared divided by 2 times 2, so r plus, no, sorry, this is not correct. So what I'm having here is just to, here I divide also by sigma squared, right? So, yeah, the whole expression is divided by sigma squared. So, if I look at the second summand, I just have, multiply it with 2 and divide by sigma squared. So the second summand is just 1, and the first one is 2r, so I have 2r plus 1. And so this just becomes b divided by s0 to the power 2r plus 1. In the second case, I just have here minus sign. I get 2r minus 1. Right? So this is just simplifying this expression a bit. So I was computing this expression here for clarity, but the second expression follows exactly analog. You just have to be careful with the plus sign here. Good. So what we get is then exactly this expression here. So this is what I was computing here. So the b divided by s0 times 2 to the power r plus 1. Is this correct? Something. Here I forgot my sigma square, right? Yeah, sorry for that. Here I forgot a sigma square, and here I forgot also a sigma square. So this is my alpha in the end. That's what is standing here. And the argument of the CDF of the normal distribution is exactly either this or this. So we have these two expressions. So the first one is exactly the probability under the measure QS, and the second one under the measure Q. Okay, I mean, in the end, everything follows from more or less the reflection principle. Good. And we have transformed this. I mean, this is a bit surprising, right? That you get an analytic solution for this kind of, I mean, at first sight, yeah, a bit strange-looking barrier option, which is exotic, which depends on the path, and so on. But in the end, we were able to more or less transform it into almost a European kind of option, at least from the shape of the formula we get for the price. Okay, the next thing we consider is, just want to discuss briefly. I don't want to prove it or anything. Just to tell you, there's also a PDE approach you could pursue to get a computed price. I mean, even though you have an analytic formula, you still can solve a PDE to get the price. And I mean, if you follow the typical arguments, I mean, replication arguments and so on, then before the option dies or becomes activated, so before knock-in or knock-out, whatever, here we consider knock-out, but you could also consider knock-in. Before knock-out, so before some event, of course, I mean, the price of the option is not zero, it's not the price of a call option, it's not clear, so it's something we want to compute. And the price evolves according to the Black-Scholes PDE. Right? The question is, how is it different then from the price of a call option, let's say? And the answer is, of course, this enters somehow through boundary conditions and also through the solution domain. So in the case of a knock, here we have, did I specify whether it's upper boundary or not? I didn't, right? So this is knockout. As soon as we hit the barrier, the value becomes zero. So this means we are considering the situation of an option that is still alive before it has been knocked out, and then, let's say an upper barrier, yeah, in this case it would be an upper barrier. So you see this from the solution domain. No, this is a lower barrier, sorry. So we are solving it from the lower barrier until any value that is larger than the upper barrier, right? And as soon as we hit the lower barrier, the value becomes zero. So this means exactly at the boundary, so this means ST is B, so this is what B in the second argument means, the value should be zero, because we knock out the option. Okay, the solution domain, this consideration, of course, is only true if we are before a knockout. Right? After knockout, the value is zero. So we don't want to compute it after knockout. So this is only true before a knockout, so only for values larger than B. And the final condition would then be exactly if we survive until maturity, we get the payoff of the vanilla option. So this means at maturity on this solution domain, we get the payoff of the call option. So it's very interesting, right? Because it's more or less always the same thing. You always have the Black-Scholes PDE, and the different specifications only enter through something like boundary conditions and solution domains. But apart from that, it's very nice that you more or less have a consistent formulation for everything. In the case that we have a knock-in option, it's a bit different, right? If we have a knock-in option, this just means that as soon as we hit the boundary, as soon as we hit the barrier, the option becomes a call option, for example. This means the condition here would not be that the value is zero, but the value would be the same as the let's say, the Black-Scholes price of a call option, given the parameters there. Right? So then we would convert it to a regular call option, and we could not distinguish it anymore from a European call option after having hit the barrier. This means in knockout case 0. In the case of a knock-in option, we would have a boundary condition corresponding to conversion to a regular European option. Okay, so I just have 2 more slides. And these are just like easy consequences of barrier option pricing. So here we have the situation that we're considering some down and out option for some payoff phi. Phi could be a call option, phi could be a put option, phi could be anything else. And if we now want to price some down and out option that has a different payoff, but is a combination of, let's say, some phi and some psi, or a linear combination, so alpha times phi plus beta times psi, then we can just write this as a linear combination of their respective prices. So why is this the case? Because, I mean, phi is something if I start with the left-hand side, so the VDO, okay, I write down the whole package, so VTST, B alpha phi plus beta psi. And I apply, let's say, risk-neutral valuation. So this would be e to the power minus r. Here I'm considering the price at time t, so rt minus t. And here I have alpha phi plus beta psi. And for the case of knockout option, I mean, it's the same as for the knock-in option. I have to multiply this with an indicator function f. Right? And f would be something like set that the minimum, if we have a lower barrier, but it's the same for an upper barrier, the minimum of st, so we are starting at time t and looking at maturity capital T, so the minimum of all future t's should be larger than b, let's say, something like that. And now we have this kind of pricing formula, and this is linear, right? So I can also write this as e to the power minus rt minus t alpha times this one, expected value of phi times 1 f plus beta times e to the power minus r t minus t times the conditional expected value of psi indicator function f. Okay, and this is just what is standing here, right? So this then leads to the corresponding prices here on the right-hand side. Just because this formulation more or less is linear, we have also used this earlier when we were decomposing everything into these 2 probabilities. Okay, and then we also have some kind of nice put-call parity, also true for down and out, down and in options. I'm just writing it down for down and out options, but I mean the argument is pretty much the same for down and in options. So here on the left-hand side we have a put option, down and out put. Here we have a binary down and out option. Binary means it's just paying value 1 if the corresponding condition is fulfilled. S is giving you the just the underlying asset. So ST if the barrier is not hit, and C is the down and out call price. Okay, and why is this true? So I mean, if we are looking at the payoff of some put option, k minus st plus. This is just like k minus st if k is greater or equal than st and 0 otherwise. And this is the same as k minus st plus st minus k, the positive part, right? Because there are two situations. If k minus st is greater or equal than st, then here on the left-hand side we have k minus st. On the right-hand side, if k minus st, if k is greater or equal than st, this is 0, the second component is 0, and it's just k minus st. So in that situation, it's true. Otherwise, if st is greater or equal than k, the two terms cancel out each other, and we get 0 on the right-hand side and 0 on the left-hand side. So this is really the same, just by a case-by-case consideration, you can see that. This is true. And, I mean, this is the, I mean, here this is the payoff of a put. This is the payoff of a call. This is just like the asset price, and k is the strike. And now, same argument, more or less as before. So if you are considering risk-neutral valuation, you have e to the power minus rt, expected value of k minus st plus. You multiply with the indicator function f, so f being exactly the same thing as before. Then you get, simply from applying what I have written above this block here, you get k minus st plus st minus k plus, everything multiplied with the indicator function f, and then you just need to decompose, right? So this is e to the power minus rt times the expected value of k times 1f plus e to the power minus rt expected value of st 1f plus e to the power minus rt times the okay, I need some space, sorry for that, plus the expected value of the payoff of a call option 1f. Okay, and these are exactly the three components we have here. So the first one, I can write the k in front of the expected value, and then I just have the payoff of a binary option. And here, okay, there would be a minus sign in front of this expression, because I also have here minus sign and here plus sign. So this is correct. This corresponds exactly to the CDO. So this part corresponds to the CDO. This part corresponds to K times BDO, and this part here corresponds to SDO. Okay. Yeah, this is a bit messy, I'm sorry for that, but I think the argument is not too difficult. I hope you didn't get lost here on the very last slide, because this was the very last slide. I mean, just a very nice, I think a very nice exercise in the end, the whole lecture, to learn a bit about pricing of exotic options, and in the end to transform these complicated looking formulas into something much more simple, right? In the end, we have applied the reflection principle, and this allowed us to derive this analytic solution. Okay, for now, I'd say that we start with the quiz in 10 minutes, so you can breathe a bit, you can go to the toilet and everything, and then in around 10 minutes we start with the quiz. Okay, so we're gonna distribute the papers very soon. Please don't talk when we distribute the papers. Don't talk to your neighbors. You know, this is closed book, so don't use anything. Put your laptops away, put your tablets away, put your smartphones away, put your, I don't know, iPhones away, whatever. Put everything away, only pen and paper. I mean, on the paper, it stands like 20 minutes time, but it's okay. You can take until 10 if you need, so half an hour time. Only 5 questions. If you are finished with the paper, you can just bring the paper down to us and leave the room. That's okay. Okay. That's it. And please be quiet when we distribute the papers. So you have still like 4 minutes left. If you have not submitted, please come soon to a conclusion. Okay, so time is over. Please make your last cross and submit your paper now.